One of the groups that we'll be looking at throughout the semester is what's known as the symmetric group. And this group consists of permutations. A permutation is just a bijection from a set to itself. Now remember, a bijection is a function who is both one-to-one and onto, which we're going to remind you of those terms in just a second here. Here I have two functions, one called alpha, the other beta. We'll look at them independently. So here's alpha. A function is one-to-one if each of the elements in the original set maps to different elements over here. So 1 maps to 2, 2 maps to 4, 4 maps to 1, 3 maps to 3. They all map to different elements. Remember, onto also means that if you look at each of these elements on the right, they are all mapped to by something. So 1 is mapped to from 4, 2 is mapped to from 1, 3 is mapped to from 3, and 4 is mapped to from 2. So that's a permutation. So we'll put a little check mark here. Alpha is a permutation. Beta, well, if we look at that, notice that 1 maps to 3, 3 maps to 1, 2 maps to 4, and suddenly we have a little problem here. 4 also maps to 3. So right there we have two elements that map to the number 3, which means that beta is not a bijection. Okay. Now you might remember from your pre-calculus days when we would have a little function. We'd say, okay, well, let's let f of x, for example, be the function x squared, and then you'd make these little xy charts. So you go x and y, and you'd say, well, x could be -2, 1, 3, 10, and then you'd write their outputs there. The function value at -2 is 4. The square of 1 is 1, so we'll put that there. The square of 3 is 9, and the function value evaluated at 10 is 100. We can do the same thing with these bijections and make something very similar. So here we have something that's very similar to that. Our inputs are the numbers 1, 2, 3, and 4, and we'll just put the function values down here below. Okay, so in our case, for our particular alpha, 1 maps to 2, so we'll put 1 and 2 there. 2 maps to 4, 3 maps to 3, and 4 maps to 1. Now it's very easy to recognize that this is a bijection because all the numbers down here are the same numbers that are used up here, and they appear once and only once. Let's just take another example of a completely different function beta, not the same one that we have up here. But here's a new function beta, and let's write it in its similar form here. So beta maps 1 to 4, maps 2 to 1, 3 goes to 3, 4 goes to 5, and 5 goes to 2. And you'll see the same information is encapsulated in this little two-line notation. 1 maps to 4, 2 maps to 1, 3 maps to 3, 4 maps to 5, and 5 maps to 2. Now there are lots of things that we can do with these functions. One is, since they are functions and since they're bijections, they have inverses. And remember, the inverse of a function is another function that sort of undoes what the original function does. So in this particular case, we want to know what beta inverse is, if this is our function beta. Well, beta inverse is going to be the thing that maps the images, we call the sort of y values the images, back to the original numbers. Okay, so what we'll do in order to find beta inverse of 1, we'll look to see where 1 is in the bottom row and trace backwards. Well, 1 is over here, it's underneath 2. So beta inverse of 1 is going to be 2. Now we want to look for beta inverse of 2. Well, to find that, we look for 2. 2's down here, it's underneath the 5. So beta inverse of 2 is going to be 5. We'll do one more of these and then just write it in its form. Beta inverse of 3. We'll look for 3 in here. Beta inverse of 3, 3 mapped to 3, so it's going to be itself. Okay, and just really quickly, beta inverse of 4 would be 1, because 4 was mapped to from 1. Beta inverse of 5, what mapped to 5? 4 mapped to 5, so beta inverse of 5 is going to be 1. Going to be 4, sorry about that. So beta inverse of 5 is 4. All right, so this, since we're talking about groups, we now have talked about how inverses exist. Inverses exist just by basically reading this bottom row back upwards to find out what matches to that. Well, we also need to know the identity, and we need to know associativity. And we'll kind of wave our hands at associativity. We'll just kind of assume that whatever operation we define will be associative. The way we'll combine any two permutations will be through composition, when we talked about composing functions. One good reason for this is if you think about a function and its inverse, we'll just use alpha. If you take alpha composed with alpha inverse, you will always get the original element back. Okay, so for example, beta inverse maps 2 to 5, and then it maps 5 back to 2. So beta of beta inverse of 5, I think I got this backwards, sorry, beta of beta inverse of 2 is beta of 5, right, because beta inverse of 2 is 5. And then beta of 5, if you look back up here, beta of 5 is 2. The original element comes back. So what will we define as our identity element? The identity element will be the function that maps everybody to themselves. Let's practice just a minute here with a composition. We want to compute alpha beta when alpha is this permutation and beta is the second one here. We'll do it one element at a time. Alpha of beta of 2. So we go to beta. 2 maps to 5. Beta of 2 is 5. So we replace beta of 2 by 5. And then we want alpha of 5. So up here is alpha. We look for 5. 5 maps to 3. So alpha beta of 2 is 3. Continuing, alpha beta of 3 would be alpha of beta of 3. Beta of 3 is 4. Alpha of 4 is 5. Alpha beta of 4, beta of 4 is 3, and then alpha of 3 is 2. Now, because this is a permutation, there's only one possibility for where alpha beta sends 5. It's got to be the one missing number, so it's got to be 1, but let's just check. So in this lovely two-line notation that we've developed, that's what the composition will look like. Okay, the next thing we're going to talk about is something that's very useful. It's a succinct way of writing these particular creatures. So we're going to talk about what's known as cycle notation. What we'll do is we'll follow the path of each individual element. So what I'll see is let's see, what happens to 1? 1 is sent to 4. Okay. Next, we want to know where 4 is sent. Well, 4 is sent to 3. See that? 1 goes to 4, 4 goes to 3, and now we need to know where 3 goes. Well, 3 maps back to 1. Oh. So wouldn't we just start this whole process over again? So 1 maps to 4, 4 maps to 3, 3 maps to 1, blah, 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 blah. So we have what's called a cycle here. And the way we'll represent these cycles is with parentheses. So we'll put 1, 4, 3, and then close the parentheses. And that closed parenthesis means that whatever number is here at the end, we loop back to the beginning. What we can do now is we can now look for elements that we haven't used. So I've used 1, 4, and 3. I have not used 2, so let's see what happens to 2. Well, 2 maps to 6. right? So we'll write 6 down here. 6, on the other hand, oh, well, 6 maps back to 2. And then we would go 2, 6, 2, 6. Oh, oops, that should be a 2, and so on. So we would say 2 goes to 6, 6 goes back to 2, so we close our parentheses. What haven't we used now? Well, we haven't used a 5, so let's go use a 5. Let's see where he goes. 5 maps to 8, so we'll put 8 down. Then we see where 8 goes. Oh, there we go again. 8 maps to 5, and we would keep cycling back through. 8, 5, 8, 5, and so on. So we'll put an 8 there. Let's see what number we haven't used. We've used 1, 2, 3, 4, 5, 6. We're missing 7. Okay, so what about 7? Well, 7 maps to 7. So what we can do here is we can just close the parenthesis like that. And so this is what's known as cycle notation. It's not too bad once you get used to it, but it's a very necessary skill for the things that we'll be doing the rest of the semester. Okay, we have a bit of a typo on this one. Over here, instead of saying 216, let's make this say 246. Okay? All right, so here we have two permutations that are in cycle notation. 164, 2537, and beta, which is 1538, 246. In order to find alpha inverse, we need to think about where alpha sends each individual element. Okay? So we're actually going to look backwards. Rather than saying what does 1 map to in alpha, we're going to say what is mapped to 1 in alpha. Well, in order to find out what's mapped to 1 in alpha, we need to find 1 and then look to the left. Well, there is no number to the left of 1, so we cycle back to the end. 4 maps to 1 in alpha, so in alpha inverse, 1 will map to 4. Now we continue. What mapped to 4? Well, here is 4. You look to the number to the left. It's 6. 6 maps to 4 in alpha, so in alpha inverse, 4 will map to 6. What about 6? Well, here's 6 in alpha. What mapped to 6? 1 mapped to 6. In alpha, so in alpha inverse, 6 will map back to 1. So we close that off. Now, something you might notice is that what did we do? We essentially just took the very first element of the cycle and wrote the remaining elements backwards. 1, 4, 6. Now, for the next two cycles, it's not very exciting. Here's 2. We'll start off with 2, and we say, hey, what mapped to 2? Well, we would look for the number to the left, look to the number at the left of 2. Well, that one we'd have to cycle back to the end, so that would be a 5. 5 maps to 2 in alpha, so in alpha inverse, 2 will map to 5. Oh, that looks like the same thing. And then we would do the same thing. 5, what maps to 5? Well, 2 maps to 5, so in alpha inverse, 5 will map to 2. And for the second 2 cycle there, we'd have 3, 7. And if you really want to, you might have wondered, well, wait. Over here in beta, we have the number 8. Over here in alpha, we have the number 7. Why don't we have an 8 over here? Well, these two functions are actually from the numbers 1 to 8 to 1 to 8. When you don't write one of these cycles, or one of the numbers, that means the number maps to itself. So really we could throw in an extra cycle that contains just one element, which we call a 1 cycle. Back here I didn't have a 7, so you could put a 7 in like that. So alpha inverse, we could also say that 8 maps to 8. Just for a little extra practice, let's look at beta inverse. Now, what I suggested was that instead of writing the cycle and really thinking it through, all you have to do is start with the first element of the cycle and then read the rest of the cycle backwards. So we had 1, and then if you read the rest backwards, it goes 8, 3, 5. For 2, 4, 6, we do the same sort of thing. We put 2 at the front, and then instead of saying 4, 6, we'll go 6, 4. And we can throw the 7 on at the end for good measure, doesn't matter. Now, another way you could write this, actually, is rather than write the first element first and then do everybody else backwards, you can just take the entire cycle and go backwards. So the cycle went 1, 5, 3, 8, we'll just go 8, 3, 5, 1. And the other one goes 2, 4, 6, we'll go 6, 4, 2. You might say, well, doesn't that represent a different permutation? In fact, it does not, because it still contains the same information. Here in beta inverse, 1 maps to 8, 8 maps to 3, 3 maps to 5, 5 maps to 1. If you look at the one down here, the second representation, if you start at the end, 1 maps to 8, 8 maps to 3, 3 maps to 5, 5 maps to 1. So it contains basically the same information. Okay, so what we're going to do is we're going to look at a composition of these two of these cycles, or permutations in cycle form. So we're going to write 1, 6, 4, 2, 5, 3, 7, and then 1, 5, 3, 8, 2, 4, 6. Okay, remember the compositions we read from right to left. Okay, so what we'll do is we'll be holding in our head a number. We'll look at a cycle, see if that number is affected by that particular cycle. If it is, we see where it maps to, and then we move to the next cycle to the left and try to see if that number appears in there. If we're holding a number in our head and that number does not appear in a cycle, we just move on to the next cycle. When a number doesn't appear in a cycle, we just take it to be fixed. Okay, so we're going to start with the number 1, because 1 is one of these numbers that we're dealing with here. All right, we look at the first cycle. 1 is not in that first cycle, so that first cycle fixes 1. It doesn't change the value. Okay, now we move with our current value, which is 1, to the next cycle. 1 is in this cycle, and 1 maps to 5. 1 maps to 5. So now we hold the number 5 in our head. We move to the next cycle. What's happening to 5? 3 maps to 7. Nothing's happening to 5, so we don't do anything. So 5 is the number we hold in our head. Now we go to the next cycle. Is 5 in here? Yes, it is. What does 5 do? 5 maps to 2. Okay, so now we're switching the number. We're keeping the number 2 in our head. We move to the last cycle. Where does 2 go? 2 is unchanged by 164, so 1 maps to 2. All right, now we want to know what happens to 2. So we start the whole process over again. We start at the very rightmost cycle. Is 2 in this? Yes, it is. 2 maps to 4. So now we keep the number 4 in our head. Does 4 get changed in here? It's not an element, so 4 remains fixed. Move to the next cycle. Does 4 get changed here? Nope, it doesn't, so it remains fixed. Is 4 in this cycle? No, it's not, so it remains fixed. Is 4 in this cycle? Oh, yes it is. 4 cycles back to 1. Wait a minute. We started with the number 2, and by the time we got over here, we ended up back at the number 1. So we should write the number 1 here, but that was what our cycle started with. So we'll just close off that particular cycle. All right, now we look for a number that's not been included yet. So let's say 3. Okay, here we go. 3 is unchanged by this cycle, so we move to the next one. 3 maps to 8. See that? 3 maps to 8. So now we have the number 8 stuck in our head. Is 8 changed here? It's not an element, so it's not changed. So we keep 8 in our head. Is 8 in this cycle? Nope. Is 8 in this cycle? No, it's not. So as I said, we started with the number 3. We're now at the number 8. Okay, so we start with 8 now, and we move from 8 and see what it does. 8's unchanged by this cycle. In this cycle, 8 maps to 1, so now we're keeping the number 1 in our head. 1 is not in this cycle, so it's unchanged. So we go to here and look for 1. Nope, it's not there. Over here, 1 maps to 6. So 8 maps to 6. Start the process over again. 6 in the last cycle maps to 2. We keep 2 in our head. Is 2 in here? No, so we keep the number 2 in our head. Is 2 in this cycle? It is not, so we keep the number 2. Oh, here is 2. 2 maps to 5. So our new number that we keep in our head is 5. 5 is unchanged here. So 6 will map to 5. Once again, 5 is unchanged by this. 5 goes to 3. Now we keep the number 3 in our head as we move to the next cycle. Oh, look at that. 3 goes to 7. So now we're keeping 7 in our head. 7's not there, so this leaves 7 unchanged. This cycle leaves 7 unchanged. So we end up with 7. Seems like we're filling this guy up pretty quickly. Where does 7 go? 7's unchanged here. 7 is unchanged here. 7 maps to 3 here. Let's see if there's 3 in this cycle. It's not, so we leave it alone. Is 3 in this cycle? It's not, so we leave it alone. So 7 maps to 3. Now I could make a mistake and write the number 3 here, but remember that's what our cycle started with, so we'll close that off. Now if you notice, we've got every number accounted for except for 1. We've got 1, 2, 3, 5, 6, 7, and 8. We don't have 4 accounted for, but because I've used all the numbers except 4, I think that 4 is going to map to itself, because it's got to be a permutation, right? So let's verify that. In this cycle, 4 maps to 6. Here, 6 is unchanged, so we keep 6 in our head here. 6 is unchanged here. 6 is unchanged here, and look at that. 6 maps to 4. So I said we started with 4, we end with 4. One final example. We want to find out what beta inverse alpha beta is going to look like. Okay, so for beta inverse, let's just write it out. Remember I said all you have to do is write the elements in reverse order. So let's do 8, 3, 5, 1, and then 6, 4, 2, and then beta inverse alpha. Alpha is 1, 6, 4, 2, 5, 3, 7. Uh-oh, I'm going to run out of room. And then beta is 1, 5, 3, 8, and 2, 4, 6. Whew, that was tough. All right, but fortunately, we should be able to deal with it here. So let's see what happens to 1. We'll go through this rather quickly. 1 is unchanged. 1 maps to 5. 5 is unchanged. 5 maps to 2. 2 is the number we keep in our head. 2 is unchanged. 2 here maps to 6, and 6 is unchanged here. So we left with the number 6. So now we start all over again back here with the number 6. Okay, 6 goes to 2. 2 is unchanged. 2 is unchanged. 2 maps to 5. 5 is our new number. 5 is unchanged. 5 is unchanged. And 5 maps to 1. So there we go. We're going back to 1. We'll close that guy off. Next number, we haven't used 2, so let's write 2 in there. 2 maps to 4. 4 is unchanged. 4 is still unchanged. 4 is still unchanged. Here, 4 maps to 1. 1 is unchanged. 1 maps to 8. So we ended up with the number 8. Okay, now we keep the number 8 in our head. So 8 is unchanged. 8 here maps to 1. 1 is unchanged. 1 is unchanged. Ooh, 1 maps to 6. And then 6. Oh, look at that. 6 maps to 4. And then 4 is unchanged. So we're at 4. All right, 4. Well, it happens to 4. 4 maps to 6. 6 is unchanged. 6 is unchanged. 6 is unchanged. 6 maps to 4. 4 maps to 2. 2 is unchanged. So we're back to 2, which means we have to close our cycle. Alright, now for, let's see, I haven't used 3 yet. I can really choose any number I haven't used, but I like to go in order so I remember them all. 3 is unchanged. 3 maps to 8. 8 is unchanged. 8 is unchanged. 8 is unchanged. 8 is unchanged. 8 maps to 3. So look at that. 3 went to 8. 8 went back to 3. All right, we've used 4, so we'll skip to 5. 5. 5 unchanged. 5 maps to 3. 3 maps to 7. 7 maps to 7 there. 7's unchanged. 7 is unchanged. 7 is unchanged. And 7 is unchanged. So 5 maps to 7. I think we have all of our numbers here, don't we? 1, 2, 3, 4, 5, 6, 7. And I don't count why there are 8 numbers there. So 7 must map back to 5. Let's check that. 7 is unchanged. 7 is unchanged. 7 goes to 3. 3 is unchanged. 3 is unchanged. 3 is unchanged. 3 goes back to 5. So sure enough, there we go.